Paralleling conductors of different sizes is generally not recommended due to the potential for current imbalance and overheating. The basic principle of paralleling conductors is to increase the ampacity of a circuit beyond what a single conductor can handle. However, to achieve this safely and effectively, it's crucial to adhere to specific guidelines outlined in the National Electrical Code, or NEC. When conductors are connected in parallel, the current divides between them based on their impedance. Impedance is a measure of the opposition to the flow of alternating current and includes both resistance and reactance. For direct current circuits, impedance is essentially the same as resistance. If conductors of different sizes are used in parallel, they will have different resistances. The smaller conductor will have a higher resistance per unit length than the larger conductor. Consequently, the smaller conductor will carry less current than the larger conductor. This can lead to an uneven distribution of current, with the smaller conductor potentially being overloaded while the larger conductor is underutilized. Overloading a conductor can cause it to overheat, which can damage the insulation, reduce its lifespan, and potentially create a fire hazard. The NEC addresses the paralleling of conductors in section 310.104. It outlines specific requirements that must be met to ensure safe and effective paralleling. Firstly, all parallel conductors must be of the same material. Secondly, they must be the same size and circular mill area. Thirdly, they must have the same insulation type. Fourthly, they must be terminated in the same manner. And fifthly, they must have the same length. These requirements are intended to ensure that the conductors have similar impedances, which will promote an even distribution of current. The requirement for conductors to be of the same material is important because different materials have different conductivities. For example, copper has a higher conductivity than aluminum, which means that a copper conductor will carry more current than an aluminum conductor of the same size. If copper and aluminum conductors are paralleled, the copper conductor will carry a disproportionately large share of the load. The requirement for conductors to be the same size is also critical. As mentioned earlier, smaller conductors have higher resistances than larger conductors. If conductors of different sizes are paralleled, the smaller conductor will carry less current than the larger conductor. This can lead to the smaller conductor being overloaded and overheating. The requirement for conductors to have the same insulation type is important because different insulation types have different temperature ratings. The temperature rating of a conductor is the maximum temperature at which the conductor can operate safely. If conductors with different insulation types are paralleled, the conductor with the lower temperature rating may overheat and fail. The requirement for conductors to be terminated in the same manner is intended to ensure that the connections are secure and reliable. Loose or corroded connections can create resistance, which can lead to overheating. The requirement for conductors to have the same length is important because longer conductors have higher resistances than shorter conductors. If conductors of different lengths are parallel, the longer conductor will carry less current than the shorter conductor. This can lead to the longer conductor being overloaded and overheating. In situations where it is necessary to increase the ampacity of a circuit beyond what a single conductor can handle, it is generally preferable to use larger conductors rather than paralleling conductors. However, if paralleling is necessary, it is essential to follow the requirements outlined in the NEC to ensure that the installation is safe and effective. It is also important to consider the derating factors that may apply when conductors are installed in close proximity to each other. The NEC requires that the ampacity of conductors be derated when they are installed in raceways or cables with other conductors. This is because the heat generated by the conductors can raise the temperature of the insulation, which can reduce its lifespan. The derating factors vary depending on the number of conductors in the raceway or cable and the ambient temperature. In summary, paralleling conductors of different sizes is generally not recommended due to the potential for current imbalance and overheating. If paralleling is necessary, it is essential to follow the requirements outlined in the NEC to ensure that the installation is safe and effective. Consider a scenario where two conductors are connected in parallel to supply a load of 400 amps. One conductor is a 500 kcmil copper conductor with an ampacity of 380 amps, and the other conductor is a 350 kcmil copper conductor with an ampacity of 310 amps. According to the NEC, the total ampacity of the parallel conductors is the sum of the individual ampacities provided that all the requirements for paralleling are met. In this case, the total ampacity would be 380 amps plus 310 amps, which equals 690 amps. However, since the load is only 400 amps, it may seem that the conductors are adequately sized. However, the problem arises from the difference in resistance between the two conductors. The 350 kcmil conductor has a higher resistance per unit length than the 500 kcmil conductor. This means that the 350 kcmil conductor will carry less current than the 500 kcmil conductor. The exact amount of current carried by each conductor will depend on the specific resistance values, but in general, the smaller conductor will carry a smaller share of the load. If the 350 kcmil conductor is carrying less than its rated ampacity of 310 amps, it may not seem like a problem. However, the 500 kcmil conductor will be carrying more than its rated ampacity of 380 amps. This can cause the 500 kcmil conductor to overheat, which can damage the insulation, reduce its lifespan, and potentially create a fire hazard. Furthermore, the uneven distribution of current can also lead to voltage drop issues. The conductor carrying the larger share of the load will experience a greater voltage drop than the conductor carrying the smaller share of the load. This can cause the voltage at the load to be lower than expected, which can affect the performance of equipment connected to the circuit. To avoid these problems, it is essential to use conductors of the same size and material when paralleling conductors. This will ensure that the load is evenly distributed among the conductors and prevent any one conductor from overheating. In the scenario described above, it would be best to replace the existing 500 kcmil copper conductor with 2 runs of 350 kcmil copper conductor. This would ensure that the load is evenly distributed and prevent any potential overheating issues. In addition to using conductors of the same size and material, it is also important to ensure that the conductors are properly terminated. Loose or corroded connections can create resistance, which can lead to overheating. All connections should be cleaned tight and properly insulated. It is also important to consider the derating factors that may apply when conductors are installed in close proximity to each other. The NEC requires that the ampacity of conductors be derated when they are installed in raceways or cables with other conductors. This is because the heat generated by the conductors can raise the temperature of the insulation, which can reduce its lifespan. The derating factors vary depending on the number of conductors in the raceway or cable and the ambient temperature. By following these guidelines, it is possible to safely and effectively parallel conductors to increase the ampacity of a circuit. However, it is important to remember that paralleling conductors should only be done when necessary and that it is generally preferable to use larger conductors whenever possible. Let's delve deeper into the technical aspects of why paralleling dissimilar conductors is problematic and how it relates to Ohm's law. Ohm's law states that voltage equals current times resistance, or volts equals amps times ohms. This fundamental law governs the relationship between voltage, current, and resistance in an electrical circuit. When conductors are connected in parallel, they provide multiple paths for current to flow from the source to the load. The total current flowing through the circuit is divided among these parallel paths. Ideally, each conductor should carry an equal share of the total current. However, this only happens if the conductors have the same resistance. As discussed earlier, conductors of different sizes have different resistances. The smaller conductor has a higher resistance per unit length than the larger conductor. This difference in resistance causes an uneven distribution of current. To illustrate this, let's consider a simplified example. Suppose we have 2 conductors connected in parallel to supply a load. Conductor has a resistance of 0.1 ohms, and conductor B has a resistance of 0.2 ohms. The total voltage across the parallel conductors is 120 volts. According to Ohm's law, the current flowing through conductor is volts divided by ohms, or 120 volts/0.1 ohms equals 1200 amps. The current flowing through conductor B is volts divided by ohms, or 120 volts/0.2 ohms equals 600 amps. As you can see, conductor is carrying twice as much current as conductor B. This is because conductor A has half the resistance of conductor B. If the ampacity of conductor A is less than 1200 amps, it will be overloaded and overheat. The same principle applies when paralleling dissimilar conductors in a real-world electrical installation. The smaller conductor will have a higher resistance and carry less current, while the larger conductor will have a lower resistance and carry more current. This uneven distribution of current can lead to overheating, voltage drop issues, and potentially even fire hazards. The NEC requires that all parallel conductors be of the same size, material, insulation type, and length to minimize the difference in resistance. By using conductors with similar resistances, the load is evenly distributed and the risk of overheating is reduced. Furthermore, proper termination techniques are essential to ensure that connections are secure and reliable. Loose or corroded connections can create additional resistance, which can exacerbate the problem of current imbalance. In addition to Ohm's law, it is also important to consider the concept of ampacity when paralleling conductors. Ampacity is the maximum current that a conductor can carry continuously without exceeding its temperature rating. The ampacity of a conductor is determined by its size, material, insulation type, and installation conditions. The NEC provides ampacity tables for various types of conductors in different installation conditions. When paralleling conductors, it is important to ensure that the total ampacity of the parallel conductors is sufficient to carry the load. However, it is not simply a matter of adding up the ampacities of the individual conductors. The NEC requires that the ampacity of parallel conductors be derated under certain conditions. Derating factors are applied when conductors are installed in close proximity to each other or when the ambient temperature is high. These factors account for the fact that the heat generated by the conductors can raise the temperature of the insulation, which can reduce its lifespan. In summary, paralleling dissimilar conductors is problematic because it leads to an uneven distribution of current due to differences in resistance. This can cause overheating, voltage drop issues, and potentially even fire hazards. The NEC requires that all parallel conductors be of the same size, material, insulation type, and length to minimize the difference in resistance. Furthermore, proper termination techniques and derating factors must be considered to ensure that the installation is safe and effective.